last week, and then where we're heading for this week. So, lab lecture each week, I am most likely going to be between the boards putting information up there, and then I will use this overhead projector. For the most part, what is going on with this overhead projector is things in your lab manual. So I'm just highlighting diagrams, things like that in your lab manual, or information in your lab manual. If it is not from your lab manual and you don't have it from another source, then I will also post it on Moodle. Now I'm going to go through our flow diagrams here. This is information you have from last week that is in your pre-lab, or the information, I won't try and give all the answers away, but this is the information you're putting in your pre-lab for this week, okay? So that's why I'm not posting this document on Moodle, because you have it as another source, all right? So as a reminder, last week, you took your unknown that had a neutral organic compound in it and a carboxylic acid in it. We reacted the carboxylic acid with sodium hydroxide to deprotonate it, and then added hexane. And by doing that, we ended up with our benzoate salt of our carboxylic acid in the aqueous layer, and our neutral compound in the hexane layer, okay? We separated those during the extraction, so remember your hexane stayed, or your neutral compound stayed in the hexane that's in your round bottom flask in your drawer right now, okay? Your aqueous layer, we added HCl to it. That converted what you had, your benzoate salt, back to the benzoic acid, okay, so to your carboxylic acid. And then you filtered that with vacuum filtration, and you have your crude carboxylic acid, all right? We're going to talk about the recrystallization of it today. So this is not a full flow diagram, so don't show this for your crystallization, because that you won't get points for that, okay? You need to actually show it with the branching arrows. We're going to talk about the recrystallization of carboxylic acid today. We also will talk about the simple distillation of the hexane from your neutral compound, and the recrystallization of your organic neutral, okay? All right, so the first thing that it talks about as far as the rest of the experiment in your lab manual is recrystallization. So we need to go through some basic rules for recrystallization, and then we'll talk about some specifics for how that pertains to what you're doing this week. First of all, what we need to look at are what are characteristics of good solvents for recrystallization, okay? And this has already been figured out for you, because we tell you what solvent to use, or solvents to use for the recrystallizations this week. So these are the things that were considered, but you need to know this information in case you had to come up with your own recrystallization solvent in the future, all right? So first of all, the solid that you're trying to dissolve, so in this case this is going to be your crude product, your carboxylic acid or your neutral compound. The solid must not react with the solvent you're using for recrystallization, because that would be a real problem. We don't want a reaction here, we just want to purify things. So we do not want a reaction between solvent and solid. We also don't want to use something that would be significantly hazardous to your health, because you're potentially using not a huge quantity of it, but you want to keep things in check and not use horribly hazardous solvents if you can avoid that. So your solvent or solvent vapors should not present a significant health hazard. And then the last one, in a minute here, I'm going to flip these over so that I put it up there so you can see it. the solid that you're trying to dissolve should be quite soluble in hot solvent. And barely soluble in cold solvent. So there may be a little bit of solubility, but you want hardly anything in the cold solvent. Okay, let me switch boards. So harder. I've lost my little hook here. So what we're trying to do when we're trying to do a recrystallization is you're trying to take the solid that you want to purify. You want to get it dissolved in a minimal amount of hot solvent, okay? And then what you want to have happen is as it cools down, it crystallizes out and the impurities stay dissolved in that solvent, okay? So you want your solid to have a minimal amount of solubility in cold solvent. You want your impurities to not change their solubility. So you don't want them to become really soluble in the hot solvent and not very soluble in the cold solvent, because they'll crystallize right back out with the solid that you're trying to purify, okay? So along with this, you want your impurities should not change solubility with temperature. So that creaking noise is the heating cooling system. I'm actually kind of surprised that it's creaking right now. Usually it only creaks with heat, but apparently it's going to creak with cool as well. So I'm going to give you an example here with hot solvent and cold solvent. What are we looking for, okay? So the solid that we want to purify will be defined that way versus the impurities, okay? In cold solvent versus in hot solvent. So what we'd like to see from the solid is something like 0.1 gram solubility in 100 grams of cold solvent. But when we warm it up, we'd like something like, this is just example numbers, this is not like these are the same numbers every time. But you want a big change in solubility between hot and cold solvent, okay? So we want hardly any of it to be soluble in cold solvent, a lot of it to be dissolved in hot solvent, all right? Now the other thing that this tells you is even in the cold solvent, a little bit will be dissolved, so when you do a recrystallization, you're going to lose a little bit of your solid. You're not going to get it all back, most likely, okay? Usually kind of rule of thumb with recrystallization is you lose about 5 to 10% of your solid with a recrystallization, okay? Now the impurities, we want those to just stay, okay? 0.1 gram solubility per 100 gram solvent. Same thing over here in hot solvent, 0.1 grams solid soluble in 100 grams of, cold solvent, this solubility, the same solubility in hot solvent, right? Which doesn't look like really great solubility, but hopefully, ideally, your solid is not all impurities, otherwise we've got other issues. Ideally, there's a little bit of impurities, and this is enough solubility to get rid of them, all right? As you are doing a recrystallization, you want to, because there's always going to be a little bit of solubility of your solid in the solvent, you always want to use a minimal amount of hot solvent to dissolve the solid. So you only want to use how much it takes to dissolve it and not a lot more. In your lab manual, there is guidelines for both the acid and the neutral compound as far as how much you should use. If you feel like you've used more than that, talk to your instructor before you get too far down the course, okay? Especially with the carboxylic acid, it's easy to think you need to keep adding more, but maybe you don't, and then you get so much solvent in there that your solid stays completely soluble even in the cold solvent and doesn't recrystallize back out, okay? And then in that case, we're gonna have to remove the solvent and basically start the process again. So follow the instructions in your lab manual. If you feel like you're deviating from that, talk to your lab prof, and they'll come check things out for you, okay? All right, for the acid too, one of the things that it talks about is you're dissolving in hot ethanol for the recrystallization. Then once you've got it dissolved in hot ethanol, you're supposed to add water until you've either made it cloudy and it persists, or you've added equivalent amount of water to how much ethanol you've added. That water needs to be hot as well, okay? So you want hot ethanol, so that means it's in a container heating on the hot plate. Same with the water, it's in a container heating on the hot plate. Now you don't want to like crank the heat, it's on low heat, so it's just enough to get it heated about at the boiling point of the solvent. You don't want it sitting there boiling away because then you're just losing solvent. Same with the container you're adding your solvent to. So you'll have your solid in a container, you're adding the solvent to that. Once you've added a little bit of that solvent, you want it on the hot plate staying warm as well, okay? But don't boil all that solvent away. So you gotta be careful with the temperature, not to get too hot, but you need to keep things warm enough so they will dissolve, all right? Questions with the recrystallizations? Okay. If you have any if things aren't seeming to go like as written, then make sure you ask those questions in lab, okay? All right. The next thing we need to do this week is, after we've recrystallized our carboxylic acid, ideally you recrystallize your carboxylic acid, then it needs to cool slowly to room temperature, and you don't want to disturb it because that'll prevent the crystals from forming nicely. So what you should do is complete the recrystallization, stick your flask at the back of the hood, and just let it do its thing. Don't touch it, okay? So while you're letting your crystals cool, what you should do is set up your simple distillation of the hexane off of your organic neutral compound. And so with the simple distillation, this is a method to remove a volatile compound or solvent from a non-volatile compound. So you have hexane that you're trying to remove. It has a boiling point in the 60s. Your neutral compounds melt either in the 50s or the 70s, okay? So that's their melting point. That's not even their boiling point. So there is a big range between the boiling point of your neutral compound and the boiling point of the hexane. You also are going to use a water bath for this distillation. So you're going to make sure you're not going to remove your neutral compound with the distillation. You're going to make sure that only the hexane disappears, okay? And so the way that you make sure this happens is you are going to, I'm going to put the example of the sample distillation up here. Actually, here, before I put this up, just one note real quick. In your lab manual, it talks about you potentially needing to do a hot filtration this is what it would look like for a hot filtration. You would have your heat plate underneath here, and you would have everything heating as you're trying to filter what you're trying to recrystallize. So you'd use a hot filtration if you have something that will not dissolve and you think it's some impurity that's not going to dissolve. Before you do a hot filtration for either your carboxylic acid or your neutral compound, ask your lab prof if you need to do it, okay? If you don't need to do this, this can end up being a real big mess that is really hard to then get everything back dissolved in, because as it's filtering, a lot of times it'll start crashing out. So it mentions hot filtration in your lab manual. Just make sure to check with your lab prof before you go on to attempt it, okay? See what they say. There may be other ways around it before you try and do it. All right, so simple distillation. This apparatus is in your lab manual. You are measuring the temperature of the solvent as it's being distilled over, so that's how you know what is being distilled, okay? Or you can confirm that it is what you think it is, okay? So to set this up, and we're going to show you in lab, piece by piece, how to put this together, okay? So I'm just gonna point out some high points here, and then in lab, before you start lab this week, we'll show you how to put this together. You'll have your stir plate over your ring stand. It doesn't show it here because it kind of confuses the picture, but stir plate over your ring stand, you use your pan that you're going to put a hot water in, and then you'll put your round bottom flask that has your hexane layer in it and put a stir bar in it, okay? Then you're going to clamp that. You always clamp the flask you start with and clamp it nice and vertically, because that sets how the rest of this gets set up, okay? So clamp it, you'll put on your three-way adapter, attached to that is your thermometer. You want to make sure your thermometer is down here, under the tip of it's under the neck here of your three-way adapter, because then it's reading the temperature of that vapor as it distills up and comes over right before it is condensed. That's the temperature that you'll use to verify what the solvent is that's being distilled over, okay? And a good place to get that temperature is when it is consistently distilling. You should have a nice temperature range. Now, your lab manual says you should collect the temperature at the first drop of distillate and the last drop. Also do that as well, but sometimes those numbers vary a little bit from the solvent temperature boiling point versus the middle when it's consistently distilling. That should be pretty much the same as your hexane, all right? Or we're not recording things correctly, okay? Or your thermometer's not in the right place. Then we'll connect things either with our T-clips or rubber bands, and we'll show you this in lab, to our condenser. Usually for a distillation, you use the Liebig, which is the wider condenser. We'll clamp that condenser and then come down to our vacuum adapter, where we, again, hold things together with a rubber band or a T-clip, and then we clamp our receiving flask, okay? So this is our distilling flask, this is our receiving flask. Our distilling flask is where things are coming from. Our receiving flask is where we're collecting the solvent, okay? And you know the temperature of what you're collecting, or use the temperature of what you're collecting to figure out what's in here, okay? So where will your neutral compound be at the end of the distillation, in the distilling flask or the receiving flask? In the distilling flask, right? It's still going to be left behind, versus your hexane will be in the receiving flask, okay? You're going to connect water to this. So as you're setting this up in your hood, put it close to the sink. Don't set it up, you know, as far away from the sink as possible, because we need to connect water to it. So get it close to the sink. The water that goes into the condenser to cool it so that it condenses your solvent goes in the bottom. We always fight gravity, okay? So water in on the bottom, water out on top, all right? You want to make sure the water in comes from the faucet. You're going to connect a hose from the faucet to your condenser. Make sure that's on good and not going to pop off. And then also make sure your water out goes securely into the sink and isn't going to pop out, okay? Refluxes and distillations are a common way hoods get washed, because water gets popped off and then all of a sudden you've flooded the hood and hence then end up washing your hood, okay? And usually the person that gets wet with the hose that popped off is not the person that set it up, it's the hood mate, okay? So be courteous to your hood mate, don't flood the hood, don't get them all wet with the hoses popping off, okay? Before you start heating this week, we will check your apparatus, okay, and make sure everything is in good shape, okay? But be careful with the water. Water in on the bottom, water out on the top. If anything looks like it's leaking, let's change your hoses. Let's get things tight. Let's make sure things aren't going to come out of the sink, all right? Now, your neutral compound after the distillation, you're going to directly after that recrystallize your neutral compound, okay? So you're going to remove as much hexane as possible. You're using a hot water bath, so make sure, first of all, use hot tap water when you're setting that up, okay? Versus, like, you can use cold tap water, but you're just going to wait that much longer for it to heat up. Versus, you know, use hot tap water that you're going to use. It's going to take you half the time to do the distillation, okay? What you will probably see with the distillation is it will slow down the dripping, okay? When it starts slowing down, crank up the heat on your distillation to push that last little bit of hexane off, okay? Your neutral compound is very soluble in the hexane because it's just carbon and hydrogen, and your neutral compound is just carbon and hydrogen, all right? So really try and push that hexane off, because with that round bottom flask, once you're done with the distillation, you're going to add the ethanol straight to it for it to recrystallize. If it doesn't recrystallize out, it's probably because you didn't get all the hexane out, okay? So before you add that ethanol, and even before you stop the distillation, kind of look at the volume in that distilling flask. You should only have a couple grams of neutral compound in there, okay? So if it looks like more than a couple milliliters in there, you probably still have hexane you need to remove, all right, before you add that ethanol. Otherwise, you'll add the ethanol, and then we'll have to distill everything off again, and then add the ethanol again to get it to crystallize out, okay? So your neutral compound, once you've removed the hexane, we're going to add hot ethanol to it, and then we're going to let that crystallize out. Actually, you'll transfer it to an erlenmeyer flask, let that crystallize out. As that's crystallizing, go back to your carboxylic acid. You can filter that, okay? And with these recrystallizations, what you should do before you filter, we let everything go down to room temperature, and then you should cool things down in the ice bath after that for about 10 minutes. So when you go back to your carboxylic acid, get it cooled down in an ice bath, clamp it so it doesn't go swimming in the ice bath, because that'll be bad. We'll have to filter it and start over again, okay, with the recrystallization. So clamp it, get it nice and cold. Once it's cold, then we'll filter it with vacuum filtration just like you did last week. You'll have your nice clean carboxylic acid that'll then dry in your drawer. And then you will go back to your neutral compound that's slowly been crystallizing, get it cold in an ice bath, filter it, and let it dry in your drawer over the week, okay? After you have recovered your purified compounds, make sure you label them very carefully. You're going to have two white substances, probably, hopefully, at the end that kind of look similar, and it'll be hard to tell them apart, okay? And it'll be hard to tell them apart from everybody else's. So make sure you label them with your name, your section, what it is, carboxylic acid, neutral compound. Also, when you go to, we're going to show you how to collect melting points this week. When you go to do that, you want to be careful. Make sure you always put your solids back in your drawer. Don't leave them by the melt temps, because you may not be done with them, but then we find these white solids, we don't know who they belong to, and then it's hard to get them back to the owners, okay? I don't recommend storing them in the weigh boats, because the weigh boats are flimsy and they tip really easy. So I would store them when they're drying in a clean, dry beaker. So while all this process is going this week, get a couple of your small beakers clean and dry, and that's where your solid should be stored as it's drying, waiting for you to check the melting points of them, okay? And then make sure you label them well, alrighty? Okay, so melting points. We are going to identify our compounds with their melting points, right? And in general, what we're looking for, we're going to show you this week how to pack these capillaries for the melt temps, and how to use, in general, how to use the melt temps. What you're going to be looking for is you're going to pack your solid in a capillary, and you don't need a lot. The more solid you pack in there, it's actually harder to see the melting point range, so all you need is like a couple millimeters of solid in those capillaries, okay? Pack your solids in the capillary tube, then you're going to put it in the melt temp, and what you're looking for is when that first drop of liquid is observed as it melts to when the last bit of solid converts to a liquid, okay? And then that is your melting point range. So from the first drop of liquid to the last bit of solid becoming liquid is the range that you are going to be recording. And you always want to record a range, okay? You don't want to record one number. With the techniques we're using and the solids we're using, we're not using techniques good enough to get a one number for the melting point, okay? So it will be a range, all right? Now, a couple guidelines for the melting points, okay? To save yourself time, what I highly recommend doing is a fast melting point for each of your solids, where you heat it up at about 5 to 10 degrees Celsius. I'll write it this way to make it more clear. Per minute, okay? You want to do that because if you, I'm going to put the table of our possible compounds up here. Actually, here, we'll show you, like, in lab this week, you will see a melt temp that kind of looks like this. And then we will also show you how to use a different type of melt temp that involves some programming of information in there, and these instructions are by them. So we will show you that in lab this week. But here are the possible compounds you could have for your acid or your neutral compound. You do not want to start from room temperature heating these up a degree per minute, especially if you're getting down to the 3-chlorobenzoic acid that melts at 155 to 157. You don't want to wait that many minutes for something to melt, okay? So the faster way to go about it is heat it up at 5 to 10 degrees per minute, and then you will get a fast melting point range. Now this is not your perfect range that you're using to identify it. This is just the range to help you out to know the ballpark range to heat it, okay? Then I cool the melt temp to 15 to 20 degrees down, okay? And then you want to do a slow melting point range. And that's what you want to collect. So you want to collect both of these for each of your solids, a fast one and a slow. And this is where it's heating 1 to 2 degrees per minute. And this is, when you collect this range, this is what should be in agreement with the known melting point ranges, okay? But doing 2 this way will be much faster than heating everything from the get-go at 1 degree per minute, okay? When you are collecting the melting point ranges too, if you're going to do both your neutral and your acid at the same time, do the neutral first because it melts at a lower temperature, either 80 or 54, versus the acid compounds melt. I'll hold this down just a little bit. All these numbers are in your lab manual, okay? The acid compounds melt starting at 98 all the way into the 150s. So you want to do the neutral compound first, otherwise if you do the acid first and then you put your neutral in there, you might melt your neutral before it actually, like you put it in and it might melt before you actually wanted it to melt, okay? So do the neutral first and then the acid, all right? The other thing that we're going to have you do for the acid is a mixed melting point range, okay? And what you are going to do to prepare for that is you're going to take 20 milligrams of your unknown plus 20 milligrams of known acid. So in the labs, we have vials, and we'll show you where they are this week, of these known versions of these compounds, okay? For the carboxylic acid only, you're going to take a mixed melting point. So you'll collect your slow melting point range, decide which of those possibilities you have based on the slow melting point range, and I'm going to give you a couple examples here real quick. And then you will mix 20 milligrams of your unknown plus 20 milligrams of the known, and you want to crush them really well together with a stir rod. Make sure, you know, not just stir it around, but actually crush them together so they're kind of become one solid. And then take the melting point range of this, okay? So if you have two compounds that are the same, what should happen to the melting point range? Be the same. If you recall colligative properties from Gen Chem, if these are different, what's going to happen? The melting point range will go up or down. It'll depress, right? It'll go down and get more broad if it's not a pure substance, okay? So if you guess right and you're mixing with the correct acid, you will have a range that matches your slow melting point range. If you didn't guess correctly, then you will probably see melting point depression and a broadening of that melting point range because it's not the same thing, and then you need to pick again, okay? So for the acid, we do this because some of these melting point ranges, like 2-methoxy is 98 to 100, but 2-methyl is then 107 to 108, and 3-methyl is 108 to 110. They're really close together, so it's hard to just figure it out just by the slow melting point range, okay? So here I'm going to give you a couple examples of that real quick before we go. So say we have, for our first example, we have the melting point of the unknown is 100.3 to 101.2. Okay, so that's our slow melting point range. And we decide, well, that looks pretty good close to 2-methoxybenzoic acid, which its range, sorry, you can't see it up there really well, is 98 to 100 degrees Celsius. So you take the mixed melting point, and that is 99.5 to 101.1 degrees Celsius. When you compare this to this, do you think that's a good match or not? That's a pretty good match, right? I mean, it's less than a degree starting from the start and pretty much ending at the same point, so that's a pretty good match. Also, if you look at this, anything less than 2 degrees for melting point range is usually a pretty good melting point range based on the way we're doing it. So that looks pretty good and pure. So I would say that you probably guessed right and that you had 2-methoxybenzoic acid, okay? Versus, say we've got another unknown, and it's 149 to 153. And we decide, maybe that's 2-bromobenzoic acid. It has a melting point range of 147 to 150, but we do the mixed melting point, and that becomes 145 to 148. Do you think this and this are a good match? Not so great, right? Because we've depressed it. The other thing, if you look here, probably this unknown is not super pure. Maybe it hasn't dried all the way. Maybe all the solvent hasn't been removed because it's a 4-degree range, okay? But we didn't get more depression because it was already depressed, but we didn't get more broadening because it was already broad, but we did get depression in the melting point range. So that points at not a good match, all right? So after lab this week, you could, once your solids are dry, you could come to Open Lab to collect the masses of your solids. You could also start working on the melting point ranges during Open Lab once they are dry. So like if you had lab tomorrow, maybe Wednesday or Friday, you could collect melting point ranges, or next Monday. Also in lab next week, we'll have some time for people to do that, but we have, I think it's like 12 melt temps, and each of the labs have 20 to 22 students, okay? So if you do have time, it may be helpful to come in over the next week and get some of this done, all right?
Okay.